It's a pleasure to welcome Dr. Anirban Mukherjee of the AIMS Laboratory, Iowa, as the speaker for our webinar today. Anirban is a postdoctoral researcher at the AIMS lab from October 2020, and he works in their quantum information theory department. He got his PhD in physics from ISAR Kolkata, working with Siddharth Lal, who is present also, where he worked on the study of holomorphic unitary renormalization group for correlated electrons. In his PhD days, he studied quantum phase transitions and entanglement in correlated electronic models, such as two-dimensional Hubbard model, the ubiquitous Hamiltonian in quantum chemistry, and condensed matter systems. He has developed quite a few open source packages based on the unitary renormalization group algorithm, inspired by the unitary coupled cluster methods of quantum chemistry, to generate phase diagrams and the effective Hamiltonians to describe the various phases in the low energy regime. This is available also as a software platform for Hamiltonian and entanglement renormalization group studies for one-band Hubbard model for strongly correlated electronic systems. He also constructed quantum circuit description of the ground state wave function for various metallic, insulating, and superconducting states, thereby enabling a sort of quantum information-based analysis of the complex nature of the various phases. These are about the evolution of many-body entanglement in a whole-doped Mott insulator, for example, and also for D-wave superconductivity for cube plates. Anirban is very active now in research using the various quantum many-body methods, in particular the renormalization group studies of just not UCC of the unitary coupled cluster, but also the coupled cluster methods, the response functions, and the equation of motion techniques, T-matrix formalism, etc. He is an avid user of the algorithms such as the VQE, the QPE, tensor factorization and tensor hypercontractions, analysis of error mitigation, and also generation of error mitigation programs using Qiskit-Ignis and MITIC, I guess.
Yes.
He's also involved in the study of quantum imaginary time evolution, nonlinear constrained and unconstrained optimizations, and stochastic optimization. He's very well versed in various aspects of quantum algorithm and some aspects of correlated electronic states in great detail, quantum chemistry, quantum embedding, linear combination of unitaries, and open quantum systems. Anirban is going to talk today on adaptive variational quantum eigensolvers for multi-orbital impurity models. So I invite Anirban, the time is yours.
Thank you very much. Thanks for this. Thanks for this wonderful introduction. I mean, you just summarized a lot of things. Thank you. So I also so this is the work that I have been doing for the last 1.5 years in the AIMS lab, where I have been developing this adaptive variational eigensolvers, which can be useful to study multiband Hubbard models using some embedding Hamiltonian approaches. So these are my collaborators. Noah is currently a PhD student at Maryland. Joao is a postdoc in our group. Peter and Yao are Yongqing are my supervisors. So, and this paper just recently we just posted on arXiv. Just last day it appeared on arXiv. So I'll be talking about it, and yeah, let's see. Yeah, so so this talk is planned in 2 parts. The first part is going to be about the mapping of multi-orbital correlated electron models into this impurity bath construction. The mapping already exists. It's called the Gutzwiller classical quantum embedding approach. What I will be showing in this presentation is how that can be simulated on on device, and also how we can construct the ground state in the background of stochastic noise and also device noise coming from decoherence and of the 2 qubit gates. So that's the part one of the talk. Part two of the talk is where I try to take up my inspirations from my PhD problem and figure out a way of constructing an embedding approach within a set of orbitals and find and constructing an effective active orbital Hamiltonian, but using quantum circuits. So basically, uh, rather than trying to compute the effective Hamiltonian from a classical computer, here for a change, I'll be trying to show you some steps of how we can try to construct this effective Hamiltonian from a quantum circuit itself by performing some functions or manipulations on the original input Hamiltonian. So these are the two parts of the talk, and they are related. I'll try to show how they are related along the way. So the first part is about quantum material simulation, as I discussed, where I will be talking, where we're looking into the physics of d and f orbitals. They are strongly correlated orbitals, where the interactions are not only restricted to Hubbard, there is also Hund's-like coupling present, and also there are interorbital interactions present. So this problem can be broadcasted as a problem of clusters which are talking to each other. And let's say if I take a cluster of 4 sites, then they can be associated with 4 other sites, which is the bath. The bath do not interact with each other, bath electrons, electronic orbitals, but they are hybridized with the system orbitals, and the bath has a dispersion, and there is a quasi-particle set of equations. So the idea of the entire formalism is that you solve the impurity problem, you by using some variational eigensolvers, and you have to argue that why it's better than ED, and why are we not doing ED. We can understand that, and then we have to we have to use that to obtain this parameters, this D, and you feed that back into the bath to get a renormalized dispersion of the bath electrons. You can solve the quasi-particle equations of motion, get the new parameters, and then we can perform this quantum classical loop. So part of the master computer becomes a classical computer, and then there is a quantum computer on which the impurity problem is solved, and then you couple the results in order to get the result, in order to get the result for the full lattice. So this is being done now for this multi-orbital Hubbard model, where you actually have this F electrons are this F dagger and F are the ones that correspond to the bath. Lambda I A B, this is the dispersion of the bath, and this A and B indices contains both the spin degree of freedom as well as the orbital degree of freedom, all of that together. And this basically DIB is the hybridization, and this HI lock contains all the interaction terms. So this is the problem, this n site n impurity problem, which we want to solve, n site n bath problem, which we want to solve using some kind of a variational quantum algorithm, because a small embedding problem. So if we can solve it using this, then we can feed that results back and get the result for the full problem. So that's the idea. So the idea basically originates from the fact that there is a well-known, now well known, it was just got invented in 2019. It's a variational quantum eigensolver ansatz, where the ansatz is not a fixed one. It is something that adapts itself with the problem. And when VQE first got created, there that point of time, the ansatz was it may not have any connection with the problem that you're trying to solve. But here in this adapt VQE, the idea is that you have a pool of operators like O1, O2, like this, and then this operators, you can feed it to the original circuit. So this blue one blocks represent the gates. So let's say you plug in one of the other gates associated with this O1, O2, which are the unitary operators, then you can see that how the energy landscape is sharp or not. If the energy landscape is a sharp for a certain class of operators, then those are the operators that are expected to bring about the the best lowering of energy at a given step. So that is what is given by the energy gradient. So you take one of the operators that within the highest energy gradient value, if the one that it will correspond to, you plug that it into ansatz. Then you perform a classical optimization, but at every step you measure the energy on the device, on the quantum device. So basically the idea is that Shy-Ket and Shy-Bra, the sandwiching, that part is being done on the device, because otherwise that calculation, if for large n, can become really complicated. So that is where we are actually utilizing the device only there, at least in this adapt VQE type calculations, and also other kind of VQE type calculations. This is where only where the device gets used. But the results get transferred to a classical computer, where the classical computer would try to find out the next available value of theta parameters, which are multiplied with each of this 102 generators in the ansatz as exponential of I01 theta 1, like that, as a product. So in that way it will try to do, and in this way we can construct an ansatz. This is well known, but the problem is that these operators can be many in number, because there is no such specific restriction on the operator set. So apart from the fact that there have to be some symmetries they have to maintain, like time reversal symmetry. So those are the only things that are there. So what we came up with, and which is the main result of my work in this part one, that is the fact that there is a way of constructing the pool starting from the Hamiltonian. Basically, uh, one requirement in this adapt VQ ansatz is that every operator has to have odd number of Y gates. Why is that? That is because the state, ground state, and your reference state, both are real. It's expected, because the Hamiltonian is Hermitian, and it is not only Hermitian, it's actually real. So if the Hamiltonian is real, and if the reference state is also real, then the expectation is that the H comma O commutator can only give you a real component if O is real. But O can only be real if this you have so O is basically I into Y. This pool is made up of anti-Hermitian operators, anti-Hermitian generators. Y is Hermitian, IY is anti-Hermitian. So this only one anti-Hermitian generator is actually purely real, and that is IY types. So that means you need odd number of Y gates in order to perform this. So that is the only restriction. So what we understood is that never in a real Hamiltonian can you have a term which has odd number of Y gates, because if there will be, then it automatically devalidates the point that H is real. So which means that you cannot take the operators from H and construct your ansatz. But interestingly, we know that in Trotter, for example, when you try to expand exponential of IHT, you actually open it up into different terms and group them, and there actually that type of a Trotter decomposition can be useful to reach a ground state. So then where is the catch? The catch is actually that when you try to reorder terms, then you generate commutators between different parts of the Hamiltonian. And those can have odd number of Y gates, even if the original Hamiltonian did not. So that is where actually I came up with the idea that you can construct a commutator of operators and then use that to fill up the pool. So this pool can leverage the Hamiltonian sparsity, and you can also use that as a starting point to construct in fact a pool with smaller number of operators, which is the minimal pool. And there is a proof which was given by Tang et al. That the minimal pool for an n-qubit system is 2n minus 2, that there need not be more members than that. But in the problem is that there are many ways of constructing this pool, and not all pools are, evolve in the correct energy landscape, so that you reach the ground state. They can get stuck in metastable configurations as well, and this is a big problem in all of these calculations, that most of the times they get stuck. So there is a way out that we are trying to provide by saying that utilize the Hamiltonian structure to construct the pool operators and then use that. But there are also other methods that people are proposing based on symmetries of the Hamiltonian to construct pools. specific pools for problems. But the real catch is of constructing out of 4 to the power n possible pool members for an n qubit Pauli string. uh, you need to construct only 2n minus 2 members which will work, and that is a difficult challenge to meet. So we are trying to or we show a way forward by using the Hamiltonian based commutator pool. So the another problem is with regards to this is that this specific problem that we're dealing with has one extra layer of complication corresponding to the Hubbard model, is that there are extra off diagonal terms. So when you're trying to estimate the Hamiltonian, you need to measure everything in the z basis, because otherwise how will you measure the expectation value? So now there are ways to do it. So the most evolved way of doing it is basically Cholesky decomposition and or tensor factorization, and you can use that to break down the 4 Fermi tensor in terms of three rank tensors, and then you do a diagonalization to get a purely z basis. So you are diagonalizing different parts of the Hamiltonian using different unitary operators. So let me show you how that works. So for example, this is the hybridization term between this impurity and bath electrons. So this is given in this following manner. You can use a simple unitary rotation, which is a single body rotation, and you can end up with purely number diagonal terms, which in the Jordan-Wigner or parity encoding represents Z gates, just single Z gates. Now, you can then consider, let's say, the V alpha, beta, gamma, delta, the 4 rank tensor. Now, this for our specific problem is one part of the Hund's interaction, which is the 4 Fermi term of this kind. This is basically a 4 Fermi term because you can open up the squares, then you can find that they will get a 4 Fermi term from it. So now, but it is written in a manner so to represent the first layer of factorization, which is the Cholesky decomposition. And the second layer is to further diagonalize that to get purely Z terms. So basically from here, you'll get single Z and 2Z type terms. So again, Z type, again diagonal gates. But every time you're having to impose an extra unitary operation set on the circuit to measure finally in the Z basis. So I'll show that. The third is if the terms are already diagonal, we do not need to perform any rotation. We can just measure the diagonal terms by itself. So in this way, we have the coupling terms, we have the Hund's terms, and then we have the diagonal terms. So that's the situation, that if you have a chi naught, then if UG is your ansatz that you're trying to construct, let's say you have constructed up to a certain number of layers, then you can put a U naught at the end and measure the coupling terms. You can put U1 and measure the Hund's terms, and then you can just directly measure the diagonal terms. So basically, you need 3 copies of this circuit, and you can every time measure this 3 to get the estimate of the Z values. Because after you do this gate, you just need to measure the Z counts for each of these qubits, and from the statistics, you can build up the energy for each of these parts. So this is the prescription, and this was given. This is highly inspired from quantum chemistry, but then it was used in quantum information recently in 2018, and then there was a Nature Quantum Information paper in 2021 where they actually compared different ways of measuring, and they showed that this way of measuring allows us to measure fully diagonal ZZ gates, and that's the part. So then what we also do is that we study now this model, which is this EG model, which is a there are 2 sites and there are 2 baths. So there are 4 sites corresponding to 8 spin orbitals. We use parity encoding, so there are effectively 6 qubits that it maps to on device. So first we do state vector simulations where we do not basically use the circuit to measure on the device, but first we try to do a classical simulation on our computers to check which among the various kinds of ansatz performs the best. So there are 2 criteria that we use. One is the number of parameters, and another is the number of CNOT gates. The number of parameters in this model is equivalent to the depth of the circuit also. So what we find is that among the four methods that we do, we use one is we do just a single UCCSD unitary couple cluster, which we construct using a single a single trotter step. We just use a single trotter step. We put in the Z gates first and then the off diagonal ones, and that's we do in terms of singles and doubles. And then we also compare it against this adapt uh, adapt UCCSD, but here we use paired doubles. So the nice thing is that if you use paired doubles, then the number of operators in the pool uh, reduces from n to the power 4 to n. So it is a n squared. So it's a huge complexity reduction. So that's why we use this adapt. Then we also compared with adapt 8C, which is the construction of this paper, which is a new construction of this paper. So this is where we compared with this. And then we also compared with the standard Hamiltonian variational ansatz, where you directly take terms of the Hamiltonian and inspired by the Trotter decomposition, you put it in different parts, but use different angles, unlike Trotter, where you just time is the only parameter. But here you use different theta parameters for the different parts. So these are the four methods that we have used. And what we find is that the adapt 8C, which is the method of this paper where we use the commutator pool, that performs relatively well in terms of the number of CNOT gates. In terms of parameters, it is more, but HVA has the least number of parameters, but we find that HV has slightly more number of CNOT gates compared to the adapt 8C technique. Whereas you can find that the UCCSD ansatz, that's pretty far away. We have not checked layered UCCSD. They might perform better. We just checked UCCSD. Layered UCCSD is inspired along the lines of HVA, so they can still do it, but there will be more number of CNOTs that are getting used in the UCCSD. So this adapt 8C techniques performs better, but there is a slightly more number of parameters, but that's about the coming from the fact that you are doing this in terms of individual Pauli strings, where when you're doing HVA, you're having, when you're applying the circuit, you're actually having a sum of operators. So that's why it's more complicated, and that's why the number of CNOT goes up. So now this is the EG model. We also studied another model, which is the T2G model, which is corresponds to 12 spin orbitals. Why? Because there are 6 sites, so 12 spin orbitals, that's why. So then here also we find that the HVA and the adapt HC both perform much better than the standard adapt and UCCSD. But again, here we find that the adapt HC gives a slightly better performance than the HVA ansatz. So these are the two analyses that we did on the state vector. Then we understood that, okay, we will take one of the methods and we'll try to see whether we can, whether this technique can survive at all in the background of noise, or it just gets washed away. Because at the end of the day, the main goal is to run it on a device. So we are trying to get step by step closer to that. So these results are again not on a device directly, but on a simulator where the quantum noise is accounted for. It's present within Qiskit. It's called the QASM simulator. It's a quantum assembly level language. It is written in terms of that, where all the Clifford representation of the entire circuit is given. So that is run, and we find that indeed there are a lot of fluctuations, because we are using this 2 to the power 12 set of measurements. That is the number of shots. They call it the number of shots, is the number of measurements. So, and we basically are trying to track the energy convergence with the number of parameters. So this here actually we also plot the fact that whenever an operator gets added, then also the parameter optimization needs to be done, so that that entire thing is being accounted for. So we perform the optimization using something called the sequential minimal optimization, where you optimize one parameter per step, and then you just keep on going for the next parameter. So what we find is that if you increase the number of shots by 4 times as it's here, then the energy spread actually lowers by around 4 times. As you can see, that the orange, this red curve is more sharper corresponding with respect to the orange curve. So we also, what we did was that we actually, this energy is estimated from the statistics. What we decided that we have got the parameters now from the energies that are estimated from the statistics. Now we'll take those parameters and we'll check that on the state vector simulator, what is the actual energies. And we indeed find that the red and the green curve both reach chemical accuracy. I mean, the energy difference between the expected state and the energy difference between the observed state from the calculations. If you took the energy difference and you plot in the log scale, you will find that both the red and the green curve are almost close or get below 10 to the minus 3. The other curves are a bit above. So basically, at least we can say beyond 2 to the power 14 shots, we are able to reach 10, the, the 10 to the minus 3 level. It's at least good for ground state energy estimations. For spectroscopy and other things, maybe we need even higher precisions. So there, the number of short numbers need to go up then. So yeah, so that's the result on the chasm simulator. Then we also study the fact that, okay, if so, if there is this pools, then can we construct smaller pools as I suggested? And can we still optimize? Because you see that one big problem in this entire thing is that there is an overhead cost of finding out which operator to add at every step and then perform the optimization. That finding that operator would also involve using the device. So we want to see whether we can curtail that down a bit more. So the way to do it is to take the pool that we have. Every operator is a Pauli string, like a Pauli word, like something like Z, I, Y, Z, X, something of that kind. So the idea is that if we could remove the Z gates, because at the end of the day, the off-diagonal gates are the ones that can cause transitions. So if you remove the Z gates, do we still get a convergence? So that is where this orange colored curve comes from, where this orange colored curve is the optimization energy solution, which can come if you remove those Z strings, but the number of pool members becomes 16 if you do that, because when you remove the Z's, then there can be more number of members which have the same form. So then you need not keep all of them. You just keep the unique ones. So then that reduces around 40 number of members. So when it does that, we find that indeed it does it, but there is a problem that there are these plateau-like regions. And we found that if you now again construct even smaller pool, so we construct then our member of 10, that's the smallest pool that we can construct using the formula 2n minus 2, because we have 6 qubits using parity encoding. So 2 into 6 minus 2 is 10. So that's 10 is the smallest number of pools that we can construct. We construct that pool also, and we find that again there are some this plateau-like features. And we find from the state vector analysis that is actually that it gets worse or it becomes more difficult to converge when you have the smaller number of members. It does, but it requires more number of parameters. So what we understand is that there is a trade-off. There's a trade-off between pool size and sensitivity to stochastic errors. What I mean by that is that if the noise is higher, then you cannot track this plateau. You will get stuck. So that means you need to have a particular threshold noise in order to overcome this barrier, and then it comes down to a lower energy. So this does not appear when you have a higher number of members. The connectivity between the operators is better, but you have to pay an extra overhead cost. So that's the trade-off. That is, if the pool size decreases, then the sensitivity, when the pool size decreases, and the sensitivity also increases. So that's the result that we got. Then we finally wanted to know, okay, we have got the results using state vector. We got the results on our chasm simulator where the stochastic noise was concerned. How about device noise, the most difficult challenge? So at least in this work, what we did was that we said, okay, we have got the ground state from the stochastic uh, from the chasm simulator. What can we do is that we can just take the ground state answers that we got there and estimate the energy on a real device. So what we did was we implemented it thanks to the quantum researchers program within IBM. They gave me some time to actually work on this device, the IBM Q Casablanca. It's a 7-qubit device. So this device has this has this kind of a topology. Not all of them are connected to each other. So 0, 1, 0 is connected to 1, 2, and the other member. 2 is connected to 4 and 3, and 4 is connected similarly to 2 and 5. So they're not all connected to each other, which means that if you want to implement a gate between 1 and 2, you need to implement two swap gates. One goes to, one swap gate, one goes to 0, and then a direct gate can be implemented in 1 and 2. So that means what is basically being told is that every time you try to do this, you will have to use one swap gate. But every swap has 3 C nodes, which means the C naught count that we got in the last calculation, which we showed, was done with the assumption that we are able to simulate on a fully connected device. But till now, there are only two companies which do that. One is IonQ and another is Honeywell, and they have this fully connected topology. I did not work on that. I worked on this IBM Q Casablanca. I mean, we need to get credits, or we have to basically put a project proposal for that. So we are planning on that. But for now, I did it on this IBM Q Casablanca, where all of them are not connected to each other. So there actually this we estimated the energy at 3 noise levels. So there's something called zero noise extrapolation, where you take the original gate, let's say G, that constructs the ansatz, then you fold the gate. Like G gets replaced by G, G inverse G. G inverse G is equivalent to G when the G is precisely implemented. But if G has errors, then so does G inverse, which means G inverse G is not identity then. So then you have some extra error that it builds up. So what we found is that if we estimate the energy at different noise levels, then we found that the energy actually is going up as expected, because it should be more deviated from its original value. So we do that. Then we perform the zero noise extrapolation using the METIC package. And then we find that try to extrapolate the energy and find out what is the energy value at this lowest energy, at the lowest noise level. That's at 0. And then we find that, okay, there is a lot of discrepancy, because this red line is what is the expected energy, and this is where we are. It's pretty bad. But then we find that we actually perform this entire set of experiments for 10 times, and then we find that when we measure a somewhat more precise expected quantity, which is the number of particles and the net spin, because of the Hamiltonian symmetries, we know that the number of particles should be 4 and the spin should be 0. 4 comes from the half filling constraint, and spin equals to 0 comes from the spin conservation in the z direction. So that's where we try to filter out the measurements and find out which are the ones that perform better in terms of respecting the symmetries. So we find that among them, 5 of them perform better compared to the other 5. So we do another calculation where we take only those 5 and perform another level of zero noise extrapolation. We find that the energy results do get better. So finally, we report that among the 10 runs, only 5 of them is the optimal subset. So, and then we take that and we estimate the energy, we get a 0.7% error compared to the exact value. So that is the percentage error that we get in the energy prediction. So our next hope is, which is the part of a future work, is to run the entire calculation of ADAPT VQE, not only measuring the final ground state answers, but measure the entire calculation on the device. The reason we did the ground state, because that has the longest circuit. So if it passes the test, then so should all the intermediate steps. So that is the expectation. But definitely this error will lead to effect in the gradient estimation as well, which means there will be effect on the construction of the circuit. So we need to do more tests there. So that's something for the future. So finally, my message is that ADAPT-AC allows a Hamiltonian-based full construction. There is an overall better performance as hardware efficient ansatz. Then that each calculations are robust to quantum noise, and the increase in short number lowers the energy spread. Then there is a dichotomy between pool size and the sensitivity. So if the pool size is really small, the sensitivity is higher. Then there is a symmetry based filtering, gives a better energy estimate, and that's part of my first part of the talk. So I'll just ask one question, is that how much time I have taken and how much time I've left? Then I can go for the next part of the talk. That's just 4-5 more slides.
3:35 now. And so
Okay.
you have time till at least 4.
Okay. Thanks. So I'll just try my best to wrap it up in another 10 minutes. Then you can ask questions. Yeah. So this is the other work which is inspired by my work in my PhD and also what I'm doing here. It's the effective Hamiltonian simulation. So the idea is that if you have a large number of orbitals, then as I discussed, that on a device, as the number of orbitals increases, then the noise and other things creep up, and then there is a way that the estimates of the energy can be bad. So it would be really great if we could find out a way by which we can actually partition the calculation down in a way so that we can we can actually do the calculation of the energy estimates on a system with a smaller number of orbitals, but it should still capture the essential physics of the model. So that is where this effective Hamiltonian concept is inspired, that if you have the full Hamiltonian, then let's say it can capture all the energy levels. But let's say if I have an H effective, then that can capture maybe the ground state and the lowest lying excitations. Then can that H effective correspond to studying only a fewer set of active orbitals and downfolding the effects of the other orbitals into it? Then will that help us solve the problem? So that's the motivation, but the main point is how to construct an effective Hamiltonian. So that is the work that I did here, because a effective Hamiltonian construction is also a difficult business, because it involves some inversions, some level of approximations. So if it's done for a bigger size system, it is difficult to do it on a classical computer. So can we have a circuit construction, which when in the future, in the coming, maybe in the hopefully in the recent future, when the devices will be available, then we will be able to implement this H effective calculations on the device, so that we do not have to do it on a classical computer, but rather on a device. So hopefully it will be better and faster. So that's the idea. And why such a thing necessary? Because if we can do it, then we can restrict the time evolution within the low energy Hilbert space. We can identify important parameters. We can account for multiple set of related determinants when constructing the effective Hamiltonian. We can account for universality. So those are the all the various interesting points for which we should be interested in effective Hamiltonians rather than the full parent Hamiltonians. So one of the standard ways of doing it is the Loudon partitioning, where let's say if the P is a complete active space which is spanned by the slitted determinants built from n active space orbitals, then that is the subspace which you're interested in, and Q is everything else. Then we can partition the Hamiltonian as a 4 blocks: HP, HQ, HT, and HT dagger. And the point is that if we can find out an effective Hamiltonian's equation, which is H effective psi is E psi, when then this H effective will act only on the orbitals that are present within the P, which will hopefully be less than the total number of orbitals. So there are two ways of constructing effective Hamiltonians, broadly speaking. One is the Feshbach-Loudon approach, another is the Bloch-Branda approach. The Feshbach-Loudon approach has an explicit E dependence in the effective Hamiltonian. In the Bloch-Branda approach, you solve a Bloch decoupling equation. If you can find out the wave operator omega precisely, then you can get the Bloch-Branda effective Hamiltonian from there. So these are the two approaches, of which the first approach is what I'm going to restrict to in this particular discussion, where you have GQ as 1 by E minus HQ. That is and there is a problem of denominator inversion. So we need to account for that in this, and then we have to find out how to construct this effective Hamiltonian on the device. So there is a very well-known architecture which has been which has been really used. It started in 2017. The paper got published in 2019, but there were a set of works that started from 2017 itself. And right now it's used in a lot of problems. It's called this method of cubitization, which is a way of estimating the Hamiltonian more directly than what a Trotter plus phase estimation would do. So the approach is that you have one ancilla which measures same way as phase estimation. It's the same, but unlike in the phase estimation, you do not measure using exponential of IHT, that exact time evolution operator. What you do is that you invoke another set of cubitization ancillas to prepare the parameter space which is contained in the Hamiltonian. So let's say if H can be written down as a linear combination of unitary operators like this, where lambda L's are coefficients and UL's are signed multi-qubit Pauli strings. So lambda L's are created in such a way that they're all positive, and all the signs and complex coefficients are incorporated within UL. So to keep lambda L purely real and positive. So with that, actually, we can construct a state on the qubitization ancillas that will store all the parameters of the Hamiltonian, and that's called prepare H. And then we can also construct the select H, where all the unitaries will be kept. Then the idea is that we can use prepare H in a controlled manner on the ancilla, and then we can apply select H on the qubitization ancillas on the system. Then we can perform an inversion about prepare, and then using that, we can use prepare dagger, and then we can use a Hadamard, and then measure. When we measure, what we actually measure is a quantity exponential of I cos inverse H by alpha. So if you open it up, you find that it's H by alpha plus I square root of 1 minus H square by alpha square, where alpha is the one norm of the Hamiltonian. One norm means that if you sum up all the lambda L coefficients, then that is the one norm. So basically, H by alpha is an is a is where you take the Hamiltonian and you divide all its parameters by the sum of all the coefficients. So that's the thing that you can directly access. So you can directly access the Hamiltonian. So that's interesting now, because if you can directly access the Hamiltonian, which was not given by earlier phase estimation, then we can take this and try to reconstruct functions of this, multiply them, and try to see whether we can construct the effective Hamiltonian. So that is the construction that I try to do, where I can engineer subparts of the Feshbach-Loudon Hamiltonian. Basically, there is one part of the circuit that can construct the off-diagonal term that couples the subspaces P and Q. There is a part that that contains the denominator of the green function, which is preconditioned in terms of the diagonal part and the off diagonal part. So this can be written down in terms of the diagonal and the off diagonal part. The diagonal part can be precisely inverted, and then we can implement that on the device using an extra set of ancilla gates, and there we can choose from the, with respect to the multi-reference scheme, which are the important configurations that we want to keep, and which are the excitations on top of which we want to keep. So there we can keep M particle excitations and these later element configurations, and then we can apply the inverse of the gate, HT dagger, and then we can measure. Then what comes out is actually, if you estimate it, then you get the expectation value of the effective Hamiltonian. So which means that you inputted parts which are acting on the full system, but the estimated part is acting only on a subpart of the system. So then you are actually able to contract your problem down to a fewer set of active orbitals. So currently the work is undergoing here, where I'm trying to now act it on a given problem and show what are the advantages, because what is the problem is that when you try to solve it in this way, you get an E-dependent Hamiltonian, which means that we need to combine it with the adapt technique to actually determine the ground state energy of this effective Hamiltonian. If that is not E, we feed it back, then we construct a new effective Hamiltonian and we again construct it. But every time we only measure on a fewer set of orbitals. This is helpful because that means we'll incur lesser amount of errors, hopefully, when we are measuring it. So that's the way in which I connect up my part one and part two of the talk, where I try to use the approach of effective Hamiltonian construction along with VQE to see whether we can leverage the advantage of an effective Hamiltonian. That's the point. So the main message is that effective Hamiltonian simulation here we are performing with an additional set of log n qubits, where n is the number of system qubits, and then we engineer different parts of the Hamiltonian so that we can construct the Fishback-Loudon form. Then we can combine the effective Hamiltonian construction with adapt VQE to determine the ground state repeatedly. This would fully determine the effective Hamiltonian once the convergence is reached. And the effective Hamiltonians have a smaller norm. So therefore, once we construct the effective Hamiltonian, when we construct the time evolution, it will be further easier for us, because the set of states that it will span is only the low energy subspace. It will not take account of all the energy states. So that's helpful. So with that, I just end my talk. These are my colleagues. Yongqing and Peter are my supervisors, and this is a postdoc. Joao is my friend postdoc. Noah was a PhD student, was a master student here. He went for a PhD in this year only. I thank Ames Laboratory for hosting me as a postdoc, and IBM for allowing me to run on their devices. And that's it. Thank you.
Thank you
Yeah.
very much, Anirban. So the talk is open for discussions, questions,
Yes.
comments, whatever. Just unmute and ask questions.
Okay, am I audible?
Yes, you are.
Yes.
Okay. I am an experimental physicist, and
Okay.
however, I have to say that I found your talk extraordinarily stimulating. And my question is based upon perhaps a mistaken notion, but if you may kindly clarify.
Yes.
Throughout your talk, I'm reminded of the Landau theory of phase transitions. Are you familiar with the Landau theory of phase transitions?
Yes, I am.
It's a heuristic theory of
Yes.
expanding the free energy in
Yes.
terms of a polynomial in an
Yes.
order parameter. Okay.
Yes.
And it's a heuristic model which depends on your identifying the correct order parameter. Nobody tells you what the order parameter is, but if you can estimate, you can figure out that order parameter, then this expansion of the free energy in terms of a polynomial in orders of the order parameter, there are symmetry arguments which say maybe the odd terms are not allowed. For example, a magnet, up is equal to down, so there's no odd. And then you can construct, you put in by hand something that turns out to be effectively a mean field model.
Yes. Yes.
Right? Okay.
Yes.
So am I completely on the wrong track as far as I'm concerned, that there is some similarity between what you are doing and this in kind of, it's a model where there is temperature and classical temperature, right?
Yes.
And in your case, there is stochasticity that has a quantum origin. Am I right in that?
You're right. So here in this plot, for example, which I was showing, these are completely of quantum origin. Yes.
Okay. So if that is so, then what is the dependence of error on number?
So it is this 1 by square root n.
So it's just
n is
as in everything else.
This is the only
Just
one part that is. Yeah, but this is just I mean, there are points to it what you are saying also, because what I mentioned right now 1 by square root n, that's the pure sampling noise. But in a device, when the experiment is being done, there is thermal decoherence, there is other decoherence sources also present. So that is a method still in investigation. No one has still yet done I mean, they have done gate set tomography to actually study the different sources of noise within the gates, but I do not know for sure whether the temperature aspect of it has been fully studied, because till now what they have mostly studied is coming from the fact that you are using either a superconducting qubits, or you are using
I'm not asking about the real. I'm asking about the theory.
Okay, so in that theory sense,
the theory, if I'm not completely on the wrong track, then here is perhaps a better enunciation of my question. The question is that if the error, and there is a sampling error, is this sampling error just a mathematical thing? Are your answers deterministic or stochastic? If they're stochastic, it is just because of the sampling. Is that right?
It's just because of the sampling. It's just coming from the fact that when you are estimating it, then you can only measure do a finite number of measurements. Now when you are measuring the up, what you're measuring is, you're measuring everything in the z basis. So measuring number of times the thing clicks as plus, and the number of times the thing clicks as minus, let's say, and then you are trying to measure the expectation values of zz, or z, only single z, like quantities, and then you're trying to add them up. But when you're trying to do that measurement, then there is an uncertainty associated with each of there's a standard deviation associated with each of the measurements. So that is what accounts for this noise.
Okay.
So
Okay.
it's purely sampling.
Okay.
If you do not include any other source of noise, if you just consider quantum, then noise, then it's just purely coming from the fact that there is a sampling error.
I see.
That's
Okay.
all.
Thank you. That's probably all the questions that I had in mind. So let me just get back to my favorite subject, which is an order parameter. So is there any hope of constructing something like a order parameter for this problem?
Yes. So not in my group, but the Berkeley lab, Lawrence Berkeley National Laboratory, there is a group of people headed by Birdie Jong, where they are actually looking into free energy simulations on device. So they are trying hard for that, where basically they are trying to look into the effect of temperature, but from the free energy end. We are also in our group doing that, but we are doing it from the partition function, and we are trying to do it using imaginary time evolution. But they are trying to do it using free energy and partition functions. So in their group, their free energy form, they can in principle input order parameters and try to simulate that. But that's a wonderful question, because I think that's something that has not been looked into very much detail. But given the fact that a number of well-known Hamiltonians have been written down in terms of free energy expressions, sometimes even topological states of matter also, they can be presented free energy. So it begs the question whether continuous field theories can be implemented on devices. So people have started working on it, but it's in the beginning stages. People have started trying to do lattice QFT and other things on the device. So I believe that there will be more work which will try to do continuous field theories, because when you're trying to do an order parameter, it will be probably if I think you have in mind something like a continuous.
That's correct. That's correct. You got it.
Yeah.
Yeah. That's what I had in mind. Thank you very much for your clarification. Okay.
Yeah, you have to basically make it into a lattice problem, and then you can do it on the device.
Okay.
Yes.
All right. Thank you.
Yeah. Thanks for the question. Yeah.
I see also.
I think. Yeah.
There is the hand raised by Siddhartha.
Yes.
Siddhartha, and
yes,
then CG crest, I think, is Prasanna.
Yes. Yeah.
So Siddhartha and then Prasanna.
Hi, Anirban.
Hi, Siddhartha. Yes.
Hi, Jay. Yeah, I wanted to ask this. See, these impurity solvers that you're talking about, they're also at the heart of various very successful methods like dynamical mean field theory and the cluster extension.
Yes.
So what advantage does AdaptHC offer over, over, let's say, using numerical renormalization group on a classical computer? So, I mean, I'm talking about method versus method, because certainly you are trying to do it on a quantum computer here. And let's say somebody tries to solve a similar method. Perhaps NRG is not such a good thing, but let's say some other impurity solver methods, like, they have this CTQMC method. So on a classical computer. Then how would you compare these two?
Yes, thanks for the question. So let me tell you the story. The story is that this is a test right now that I'm doing. I mean, the real goal is to go for 5 impurity 5 bath model, which corresponds to a 5-band model, multi-orbital model. Now if you try to do that, then the classical resources that are getting used are are not good, are not scalable starting from. So this is like a two band model for which this is the impurity solver that we're trying, impurity model that we're trying to use. So for a 5-band model, if you try to scale it, then the classical calculations are not scaling well. So in what we are trying to do, so first test was to check whether this 2-band model can work. If the 2-band model can be completely worked out, then the next goal would be to check that if you scale 2-band, 3-band, 4-band, 2-band, 3-band, like that, if you go on, whether those can be simulated also on the device. If they can be, then what is the advantage? So what you're asking for is precisely the question of the quantum advantage, whether at all there is an advantage or not. So that is something that still has not been demonstrated. It's just a hope. We are trying. So if the 2-band model results completely work out on the device, then the people will try to go for 3-band, 4-band, or 5-band and try to see how, because for example, as you can see, 2-band model, you have got the results done in with 200 CNOT gates, but immediately you see that 3-band model is around 2000 CNOT gates, which is huge. So which means that if I try to do 5-band, then that will also be pretty high, and UCCSD is anyway far away. So now compared to numerical renormalization group, the numerical renormalization group calculation faces an even harder task when they try to solve the impurity solver on this model. So because it's like a five impurities, and then you do not have a, so in NRG is based on the Kondo like thought, so if I'm not wrong. So there, if the impurity is like one impurity spin only, but let's say you have 5 impurity spins and then they're talking, so there you have to do this calculation repeatedly. So if the amount of time that you can run this calculation for is so as per estimates from our model is that you need to do it every 5 minutes. You have to get an answer, then you need to loop it back to the main calculation, because once you solve it on the NRG, it's not done. You have to take the result, you have to feed it back and get a new Hamiltonian, which you have to again solve by NRG. Then you have to loop it. So that
you're referring to the self-consistency.
Yes, yes. So that yes. So that intermediate calculation, if it runs for much number of time for higher band models, then it's not efficient. But then it might be that even the quantum version is not efficient. So that is what we are trying to check. We are not sure. I mean, and this is a situation in every field. I mean, no one has demonstrated quantum advantage in any field till now, except for the boson sampling problem, but no other problem. So that is why we are just trying to check whether for this multi-orbital models, the 5-band model, the 3-band, 4-band, 5-band models, they give a better performance in terms of the time taken to solve it on the device. If
but
that
how many lattice sites do you have in your bath?
So
in each of your baths, how many lattice sites do you have?
So currently this this specific method is the Gutzwiller classical embedding method, where but the idea is that if you have 4 sites in a cluster like this, this is one cluster, then you have 4 bath sites, 4 bath sites. Right, 4 bath sites. So that corresponds to so that now the biggest model that my supervisor gave me, which we solved on a state vector, but on a device I couldn't do because it just is not good enough. Right now the device coherence times it corresponds to a 20 spin orbital model, because you have 5 sites, 5 bath sites, 10, which means 20. So 20 spin orbitals. So which means if you want to solve an NRG for that, then you need 20 spins and which are probably of which 10 at least are talking to each other, and then there are 10 bars. So that's the kind of model that you want to solve. So I mean, I'm not able to calculate specifics here, but I'm just trying to tell you the problem becomes increasingly complicated. So it's not clear that whether that will help or this will help. I mean, the standard method or this, but I think people are trying from both ends. They are trying to develop classical methods better.
Thanks, Anirban.
Yeah.
Prasanna?
Yes. Hi. So my questions are more on the details of the calculation side. But before that, I am I'm very knowledgeable on this front. So I just wanted to know what is EG and what is T2G very briefly, so that I get a feel for A, how many qubits or how many spin orbitals are involved in the calculation, and B, where is the strong correlation coming in the system?
So it's coming from the fact that we are dealing with strong relations coming from the fact that we are not dealing with the S and P orbitals. We are dealing with orbitals that have this lobe-like structure with the D and F orbitals, and then this T2G and EG splitting is coming from the hybridization splitting that of the EG orbitals and the T2G orbitals. So you have the 3 T2G and the 2 EG orbitals. So that those are the EG and T2G orbitals that are here, that are involved. That is dxy. So you have dxy, dx squared minus y squared dy. So you have dz squared in the top, and yeah, I'm forgetting, but you have dx squared minus y squared and dz squared at the top. You have dxy, dyz, and dzx at the bottom. So those are like the 3 and 2 splitting that you have. So that corresponds to the EG model, corresponds to this 2, and the T2G model corresponds to 3. So this EG model involves 4 spin orbitals among these blue sites, and these Bath sites involve another 4, so that's 8. But then the nice thing is that there's something called this parity encoding, where we do not encode directly the electrons, but we encode the qubits, which are coming from the phases, relative phases. So that's why it reduces it by 2, so that becomes 6. So you're dealing with a 6 qubit model from EG, and for T2G you are dealing with a 10 qubit model. Yeah, that's the point.
Oh, I see. So sorry, maybe I didn't word the question properly. What I meant to ask is, you have the orbitals had to be a part of a system, and the reason why I asked that is because the integrals that you supply to VQE would in turn depend on the choice of single particle basis, which would then change depending on the system you choose, right?
Yes.
So
right.
that's why I was yeah. So that's why I wanted to know what system we are considering, of which you're only considering, say, the d orbitals and then making an EG model. Is my understanding correct?
Yeah, you're right. So what there is a there is a code which from where the 1 electron and the 2 electron integrals are supplied, which leads to the 8.982, and use that to construct this EG and T2G models for this d orbitals. Yes.
Sure. But what system do you choose? I mean, because let's say you take hydrogen atom, or let us say that you have beryllium atom, they will have 2 different single particle basis sets, right?
You are right. So this is not this EG and T2G models are not being done for the quantum chemistry for that quantum chemistry model. It is being done for nuclides, for iron nuclides, for that band models where there are multiple bands. So that is what's being the orbitals are being considered as EG and T2G. It's not of the quantum chemistry.
You have d orbitals which are partially filled in. You have to go to that heavy atoms. Actually.
That's right. Only the outer ones, not all of them. Yeah, only the yeah, that's right.
Okay, so let us say, for example, you take FETE or FESE that you showed in the first slide. So you take FESE, you take the say STO3G or some basis for FE and SE, get the 1 and 2 electron integrals, but when you do VQE, you select only the D and F orbitals or whichever orbitals are relevant for your EG and T2G. Right. This is the big picture. Okay, I see. And the strong correlation comes from the fact that these D orbitals and F orbitals are fairly open.
Correlated.
So it will become a highly open.
Exactly.
I see. Okay.
Degeneracy leads to strong correlation.
Yes.
Okay. Thanks. Now I understand this. Then the second set of questions had to do with more details. So the initial state that you choose in this case would be some sort of a Hartree-Fock or just a direct product of some spin orbitals? No.
So I did try both, and I found that that somehow I'm yet to find out the reason, but I think of some answers now, probably better than before, is that I did not find a good result with the Hartree-Fock. With Hartree-Fock, I found that I needed 30 more C0 gates than the one which was just a separable state. So I needed a bit more. And
you mean separable did better than Hartree-Fock?
Yeah, separable did better than Hartree-Fock, because what happened was that Yeah. So Hartree fog, the way we constructed is we used Gibbons rotations from this open fermion and plugged it as an initial gate set. Then we started applying the other gates, but then we found that it reaches the energy convergence at a low using more parameters, at least 3-4 more parameters. It was going slower towards convergence, but when we started with separable state, it was more flexible and there was no initial entanglement built in. So there it worked out better. Maybe the way this adapt VQE, the operators are being used, what operators are being used, it depends on that probably. Yes.
I see. And the last couple of questions, actually, yeah, the last couple of questions. So I just wanted to know the number of layers, because then that would translate to the cost and therefore the depth of the circuit, right?
Sure. So for the EG model, the number of layers is around 30, if I'm reading correctly, using adapt HC. Because for the EG model, so when you do adapt VQE, the number of parameters is related to the number of layers, because you're just applying one gate at a time, one multi-qubit gate at a time, and every gate is a single multi-gate. It's not a sum of operators, it's just a single operator like X, Y, Z, Z, something like that. So the number of parameters is the number of layers. So
I see. And my last question is, when you showed the results, you used some sort of a gradient based optimizer.
This one's?
Yeah, because for state vector and for noisy, we use different optimizers, right? Because they see different landscapes. So
you are right.
Did you use...
You're right.
Okay,
I use but for both of them, I use this something called the sequential minimal optimization. It's not a gradient based optimizer. What it does is that it measures two different energy points and constructs with respect to every parameter direction. It's a cosine function. You can exactly compute that, because if you have a single multi-qubit string, then it becomes a simple cosine function. Then you find out the minimum of that cosine function, and then you settle down there, and then you start again. So we do an outer loop sweep of 40 sweeps, and we run for every parameter once. We do a optimization with respect to one parameter every time. So that is how we do it. So that's a non-gradient based optimizer. Yeah, but we also tried a gradient based optimizer, but it was not precise gradient. It was this ADA delta inspired from machine learning like techniques. It was a stochastic gradient descent based optimizer. We use that and it gets similar results.
So you use the machine learning inspired optimizer for the quantum runs, and for the state vector ones, you use a more traditional kind of an optimizer?
No, for the state vector also, for the state vector, we use a traditional optimizer. For the for the noisy calculations, we use the stochastic optimizer. There, the learning rate was updating, and that kept control of this noise, and therefore we were able to get similar results to what the sequential minimal optimization gives.
So sorry for so many questions. So thank you. That's okay.
Thank you. Yeah.
Yes, thanks.
Any other question?
Yeah, this is Bhanu Das. Can I ask a question?
Yes, please.
See, the choice of the operator pool is critical for adapt VQE.
Yes, you're right.
Is this problem completely resolved by qubit adapt VQE?
No, I tried this. My work is on qubit adapt VQE.
Yeah,
but
exactly.
but it doesn't solve the problem, because even in qubit adapt VQE, the operator pool, as I mentioned, has this 4 to the power n minus the number of operators, which is even number of Y gates. If you minus that, that also is a very big number. So now from there, trying to construct the minimal pool, there are many ways. So when this Sophia economy or the Virginia Tech group first came up with this way of constructing the minimal pool, they put in the paper, but then every group tried to work on it and no one found the results. So they were all worried what is happening. And then they again tried to come up with another result in 2021, which is the symmetry avoided roadblocks based adapt VQE, but they were trying to say that given the symmetries of the problem, you can identify in a close prescription how to construct the minimal pool. So there are some constraints on how to identify a minimal pool. So we checked from our method that if you take the Hamiltonian commutator pool also, from there are many ways you can construct a member of 10, and of which some of them will pass the test of the minimal complete pool and some of them will not. But even if among the ones which pass the test, not all of them perform equally well in trying to optimize. And that is why what we found is that if you try to construct this minimal, because if you can construct a minimal pool, then your problem is solved of trying to find out the operator set. But the problem is that with the minimal pool of 10, we found one class of that where it gave convergence, but the problem is that you had a region of plateau with noisy things. So this is just sampling noise. If I put device noise, then it will be even worse. So this is the problem, that this kind of pools are good, but there is a trade-off. I mean, you increase the sensitivity to noise. So that is why what we had in mind was this Hamiltonian commutator pool, but it has its own issues, which I should mention, is that if your problem is not sparse, if it's dense, then this pool size will be big. So for quantum chemistry problems, this pool size will be still of the order of n square, or the number, because the chemistry models are dense, more dense than the models that I was dealing with. But nevertheless, we can still try to take that as a starting point and construct the simpler pools of smaller size. But it's an ongoing study. It has not been completely resolved. Yeah.
I mean, have you tried some kind of?
Please go ahead, Banu.
Have you tried some kind of machine learning to see?
Yes. So there have been. Yeah. So there are some techniques. You are absolutely right. There is something called a perm VQE, permutation VQE. It's not completely machine learning based, but what it does is that it tries to take the tries to start from some learned state, let's say some state that one gets from DMRG, for example, and it tries to measure the correlation between the qubits using mutual information as a measure. Then they try to find out among a given pool, which of the members can be responsible to recreate that entanglement. Let's say the state corresponding to DMRG, and which is a good guess state for a ground state. So then you can take that, and then if you find that, okay, this member satisfies the criterion, then you keep only that in the new starting pool. But I mean, that can be good for some models, but it is not shown that it is good for quantum chemistry models. They were showing it for some transverse field or the Heisenberg chain or the spin kind of models. So it's not solved there. Now, machine learning, not, but there is an evolutionary algorithm being used to find out that every operator can be given a score, and then trying to see whether the evolution algorithm picks out the right set of operators. The main problem is that you are dealing with operators, Pauli words here. So machine learning should give us a set of good Pauli words. I tried to think along that lines, but I couldn't figure it out. But I mean, in the literature also, people are trying different kind of evolutionary algorithms. That's the closest to machine learning algorithms that I can say that they're trying.
Okay, thank you. Thank you very much.
I can send you the list of papers.
May I ask one more question?
Yes, please.
This is Sabyasachi, but sorry again.
Yes.
You said that even without getting into real, experimental noise problem, you are finding difficulties handling just a theoretical thing. So
yes.
What are experimentalists telling you about how to think of experimental noise? Suppose, is there any understanding of what noise? Is it just decoherence problem, or there are more problems?
Yeah, that's a very, very good question. So as far as my understanding goes, and from the talks that I've been listening to, people are saying that we need the better form of an error correction, because this present techniques that are being used, like this MITIC techniques that I've been talking about, and also there are techniques based on something called the shadow formalism, where they are trying to use copies of density matrices to exponentially suppress the noise, but they require more and more number of measurements. So which means that the advantage that you would want to get from a quantum device, that would be nullified from the fact that you have to do large number of auxiliary measurements in order to correct your measured data. So it can be post-processing, but then also you need to measure an auxiliary set of measurements. So therefore, they are saying that probably the only way forward now from this mess is to have cat-like concatenated states to represent effective logical qubits and use that, so that basically they're saying that given that it's a very big hardware problem, we need to come up with different ways of quantum error correction, where we figure out ways of encoding a large number of qubits into an effective qubit, and then use that to simulate. Because I mean, I don't think so that there is another way out here. I mean, everybody is finally boiling down to that. I mean, but in different ways.
Yeah. No, I'm beginning to get an understanding of the scope of the problem. Not that.
Yeah.
Yeah. Okay. Thank you very much. That was very nice. Okay.
Yeah.
Anirban, that last comment you made in response to Professor Shobhushachi's question, it's kind of reminiscent of our search for the topological quantum computer, right? Because
so
you
that is
want some kind of a long-range entanglement to give you robust quantum.
So that is Microsoft's bet. I mean, I can share the YouTube link also. I mean, there is a kind of a weird conversation. I mean, you can check between the Station Q head and Shankar Das Sharma, where they are saying that Microsoft has probably solved their Majorana fermion problem and they can construct a topological qubit out of it. But they are saying that they will not release a paper yet. They want to work on it more, but they have a lot of people who are expressing interest in that. The other approach is using this photonic based things, which Xanadu is coming up with and Psi Quantum is coming up with. But so these are the two sets of things that they're coming up with. And recently in 2022, there is a group of people, at least 3 groups of people actually, in Germany, Austria, and USA, where they're saying that they can use photonics, silicon photonics, to actually get gates with fidelity which is 0.999. But people still, they are using this topological, not topological, they are using just the standard error correcting codes. So they are making, let's say, encoding 1 qubit in 7 qubits, effective 1 logical qubit in 7 qubits, and trying to use that in correlation with other ones to measure. But Microsoft is saying that no, the topological qubit is the only way forward, and Majorana fermion is the only way forward. So I think that there's a big clash. I mean, they are not expressing not everything they are saying is not. I mean, it's not only based on science; it's also based on competition between companies. It's like that. I mean, with respect to my physics understanding, I believe that yes, topological qubits is necessary. Yes, that's all I can say.
Thanks.
Any other question? I have a kind of a short technical question that the Lovedean partitioning requires the inverse of E minus H.
Yes.
Now, okay, iterative and basically big matrix inverse. Now, you mentioned also simultaneously the block partitioning, block Brando. Why not use block Brando? Because it has 2 advantages. One is the energy independence. The other advantage is that it has a clean equation for the wave operator, non-iterative.
Yes, you're right.
Operator. So why not use that? And it has also a direct correspondence with coupled cluster theory, which is very powerful and very well developed.
Yes.
So why not use that?
Yeah, I mean, I was not that associated with this block Brando formalism, but I did study the decoupling equation before. So my only thing is that in order to determine the H, you need to solve the decoupling equation. So there you need a form of this omega, and then you need to.
Oh, of course, you need the form. But
yes, you need the form.
That's coupled cluster, for example.
Yes, you need the coupled cluster form of the omega, and
for
then
example,
you can solve.
There could be others, but perturbative also. For example, coupled cluster, yes.
Yes. So there you need to solve for the the coefficients, and there again I believe that such a calculation which I was trying to implement can be useful. But it's just that here I was able to, the way I was solving it there, I was able to directly map it onto an effective Hamiltonian, which was dependent on E, but it was an effective Hamiltonian. So I would say that I was able to say that I can use either VQE or phase estimation to estimate the energies. So there I have to find out how to solve the decoupling equation and use the estimates of the expectation values to determine the parameters of the which define omega. So
well, I mean, the decoupling equations are they come from many-body theory. So,
right.
for example, for the couple cluster, the decoupling equations are the couple cluster equations. I mean, they're known; they are clean equations.
Yes.
You have to make approximations, maybe. That is certainly possible, and these are done essentially. So I can see Dr. Kenji Sugisaki present here in the audience, and who actually has been working on multi-reference formalisms in the context of quantum computational strategy for quite a few years now. I don't know whether Dr. Sugisaki would care to respond. I don't know whether he listened or he got it.
Yeah, will be interesting to check, because my plan is to check that. I have done this part, but my plan is to check that and compare and come up with the final answer. But yes, it will be really great to see if we can use the technique like cubitization to actually construct an architecture that actually is able to determine the omega from the cluster equations, and then we can use that to construct the effective Hamiltonian.
Qubit couple cluster theories exist.
Sorry?
Qubit couple cluster theories exist, but I'm not quite sure whether they correspond to what you are telling. I do not know enough about quantum computing, so I cannot tell that, but I have seen.
So the qubit couple cluster theory, they are probably so so there is this qubit couple cluster theory where they're actually replacing the Jordan-Wigner strings in terms of QX and IQI, like that. I mean, X and Y gates.
Right.
And but that is different from this. They are just trying to then after that just trying to do the standard VQE with that. It doesn't really. This is different. Here I'm trying to say, if I can construct the effective Hamiltonian itself, which acts on a lower number of qubits, and then use that to perform Hamiltonian simulation, like using time evolution, determine the response functions from there. So that is my goal. So there definitely, if the omega operator can be determined using qubitization, then we can use that also, where the E dependence will not be there anymore. And then we can use that to construct an effective Hamiltonian and solve that same problem. So yes, that is definitely something which is on my list, and I would love to do it and try to understand the knowledge of that. Yeah.
Okay. Many thanks. Any other?
Just a comment again from Hanudas. Yeah, maybe quantum annealing might be a viable option for the effective Hamiltonian that you're thinking of.
So yes, so my goal was in two parts. One is to just calculate the Hamiltonian, but then I know that there will be iterations needed to find out the right effective Hamiltonian in the subspace. So there I have considered currently the two things. One is this phase estimation, and another is this variational quantum eigensolver. But I will think about annealing as well, whether we can implement that to get the effective Hamiltonian. Yes, absolutely. I have to check that. But I have still not think about the phase estimation and the variational eigensolver like techniques. Still now I've thought about those two. But yes, I will again also think whether we can use the D-wave like systems. They use that. So yeah, can try to do that as well. Yes, why not?
Do they use it for degenerate problems also?
Yes, they use it. Degenerate problems also they use it.
That I see is not very simple.
No, it's not that simple. So they try to do it, and it has been there for the, I mean, D-Wave is the oldest, so they have a lot of techniques on board already for optimization problems. So I think that's a very good point. I mean, that whether we can use, I mean, whether we can use D-Wave. Since I am into this Qiskit, so I am somehow polarized, you may say so, towards gate-based computing. But definitely one should also look into annealers. I am just polarized into gate-based thinking. That's all. But I think we should also look into effective Hamiltonians and try to open up the possibility that we can simulate quantum chemistry calculations better using annealers. Yes.
Okay. So if we don't
I have a question.
Okay, please, Bhupen.
Yeah, this is the results that you have shown is from the IBM superconducting qubit processor. So
yes.
Would your result have been different if you have used ion qubit processors?
Yes,
because
yes,
you don't have any coherence effect in it.
Yes, you are absolutely right. So if you use this ion-based computer, one big advantage is that the connectivity is purely all-to-all. Everyone is connected to everyone in the ion-based computing. At least that is so for both Honeywell and IonQ systems. So there immediately, the fact that I'm having that when I'm compiling the gate, my number of C0 gates are tripling because we are having the swaps, as I mentioned. So that will get removed. That problem will get solved. So immediately you should have a better result on the IonQ device. In fact, there is a new result which shows that Honeywell devices are performing extremely with much better quantum volume and much better than both IBM and the IonQ devices. I mean, it's still on the archive, but there are those claims. So I am currently planning to check that using this Qiskit's IonQ extension, and because Qiskit has also an IonQ extension, so you can run Qiskit circuits as well on IonQ. So I'll try to check whether we can get better results.
But the larger coherence time in the ion qubit, I mean, would it have any effect?
It will, but I'm not. I mean, it should. So I'm currently just aware of the fact that the topology is going to have a positive, very great effect. But I'm yet to understand whether how great an effect will the coherence times have. Yeah, but it should have also, because the fidelity of the gates is higher. It's like 0.992, which is greater than most of the IBM devices.
It's much better than the superconducting qubits.
Exactly. Way better. So it should have something more to offer.
Okay, thank you.
Yeah.
Okay, so we are coming to the end of this very interesting seminar, and let's all thank Anirban for a very stimulating talk, and which sort of spawned a lot of ideas and a host of discussions. So I thank both the speaker and the participants for a very lively meeting. So
yes, I also enjoyed it.
Thanks a lot. And
thank you very much.
Thanks a lot for coming and giving this talk.
Thank you very much.
So we just then